Hi guys, tonight we're taking you on the ultimate journey through time and space. What if you could actually witness the birth of the universe itself? We're talking about standing at the very edge of existence, watching everything explode into being from a point smaller than an atom. If you enjoy these cosmic origin sleep stories that explore the very foundations of reality, hit that like button and subscribe for more. And drop a comment letting me know what time it is where you are and where you're listening from. I love hearing from my community of cosmic explorers. Alright, let's begin. Imagine standing at the very edge of existence itself, in a realm where time has no meaning and space has yet to unfold. You're about to witness the most extraordinary moment in all of cosmic history, the birth of everything that ever was, is, or will be. This is not merely an intellectual exercise or a flight of fancy. This is a journey to the very foundations of reality, where the laws of physics themselves are being written in real time, where the concept of before loses all meaning, and where you will observe the universe exploding into existence from a point smaller than the nucleus of an atom. The moment you're about to witness occurred 13.8 billion years ago. Though from your vantage point outside the normal flow of time, these temporal markers become meaningless. You hover in a state of pure observation, somehow existing in the primordial void that preceded everything, a void so complete that even emptiness itself had not yet been defined. The temperature around this infinitesimal point of infinite density reaches beyond 1 trillion degrees Celsius, a heat so extreme that it would instantly vaporize not just matter, but the very concepts of hot and cold, matter and energy, existence and non-existence. In this moment before the moment, all the mass and energy that will eventually form the 100 billion galaxies of the observable universe, each containing hundreds of billions of stars, all the planets orbiting those stars, all the life that will emerge on countless worlds, all the civilizations that will rise and fall, all the thoughts that will be thought, and words that will be spoken. Everything is compressed into a region smaller than a proton, with a density approaching infinity. The gravitational field at this point is so intense that space and time themselves become meaningless concepts, twisted and contorted beyond any possibility of measurement or comprehension. Then it happens. In an instant that defies description, the universe begins. But this is not an explosion in the conventional sense. There is no blast wave expanding into pre-existing space. Instead, space itself is being created, moment by moment, as the fundamental fabric of reality unfolds like a cosmic origami of unimaginable complexity. The very coordinates that define position and distance are being established for the first time, and you watch as the architecture of space-time crystallizes around you. The first fraction of a second, specifically the first 10 to the negative 35 seconds, witnesses the most dramatic transformation in cosmic history. During this period known as cosmic inflation, the universe undergoes exponential expansion, growing from subatomic scales to the size of a grapefruit in a time span so brief that light itself would barely move the width of an atomic nucleus. The expansion rate during this period approaches 3 times 10 to the 26th meters per second per meter, meaning that every point in space is rushing away from every other point at velocities that make the speed of light seem glacially slow. As you observe this cosmic birth, the temperature begins its inexorable decline from those incomprehensible initial values. By the time the universe reaches 1 second of age, the temperature has dropped to a comparatively cool 10 billion degrees Celsius, still hot enough to prevent the formation of atomic nuclei, but cool enough for the fundamental forces of nature to begin separating from their unified primordial state. The strong nuclear force, which will eventually bind protons and neutrons together, diverges from the electro-weak force at energies around 100 billion electron volts, while the electromagnetic and weak nuclear forces will maintain their unity for several moments longer. During these first few minutes, you witness the cosmic nucleosynthesis, the universe's first attempt at chemistry. When the temperature drops to around 1 billion degrees Celsius, roughly 3 to 4 minutes after the initial moment, protons and neutrons can finally stick together long enough to form the lightest atomic nuclei. You watch as roughly 75% of normal matter becomes hydrogen, single protons that will serve as the fuel for countless future stars. About 25% becomes helium-4, with trace amounts of deuterium, helium-3 and lithium-7 forming in proportions that cosmologists will later use as evidence for this very moment you are now witnessing. But the universe at this stage remains opaque, filled with a dense plasma of electrons, protons and photons in constant interaction. Light cannot travel far without scattering off free electrons, creating a cosmic fog that will persist for hundreds of thousands of years. From your privileged position outside normal space-time, you can perceive through this opacity, watching as the cosmic web begins to take shape through the gravitational influence of dark matter, that mysterious substance that comprises roughly 27% of the universe's total mass-energy budget. Dark matter, invisible to electromagnetic radiation but gravitationally influential, begins clustering in the first few thousand years after the Big Bang. You observe as these dark matter halos grow through gravitational accretion, creating the scaffolding upon which all future cosmic structure will be built. The largest of these dark matter concentrations will eventually anchor galaxy clusters containing thousands of individual galaxies, with total masses reaching 10 to the 15th times that of our Sun, while smaller halos will host individual galaxies and groups. The cosmic microwave background radiation, that ancient light that will eventually provide humanity with its earliest baby picture of the universe, is continuously scattering and rescattering through the primordial plasma. The temperature of this radiation bath continues its steady decline, following the expansion of space itself, according to the relationship first described by Georges Lemaitre and later refined by countless cosmologists. At this stage, roughly 50,000 years after the initial moment, the temperature has dropped to about 5,000 degrees Celsius, and the radiation density begins to fall below that of matter for the first time in cosmic history. Then comes one of the most dramatic transitions in cosmic evolution: recombination. Despite its name, this process involves not the rejoining of previously combined particles, but the first time electrons and protons combine to form neutral hydrogen atoms. When the universe reaches an age of approximately 378,000 years and the temperature drops to around 3,000 degrees Celsius, the binding energy of hydrogen atoms finally exceeds the average energy of photons in the cosmic background radiation. You watch as the cosmic fog lifts with startling suddenness. In what astronomers will later call the surface of last scattering, photons decouple from matter and begin travelling freely through space for the first time. The universe becomes transparent, and that primordial light begins its 13.4 billion-year journey across the expanding cosmos. When it finally reaches Earth-based telescopes in the late 20th century, it will have been redshifted from visible light to microwave radiation, cooled to just 2.7 degrees above absolute zero, but carrying within its subtle temperature variations the imprints of quantum fluctuations that existed when the universe was merely 10 to the negative 35 seconds old. The period following recombination, known as the Cosmic Dark Ages, spans several 100 million years during which no stars yet shine and no galaxies have formed. The universe consists primarily of vast clouds of neutral hydrogen and helium, punctuated by the invisible gravitational wells of dark matter. But even in this apparent emptiness, profound changes are occurring. The first dark matter halos are growing through gravitational collapse, and within these invisible structures the primordial gas begins to accumulate and condense. You observe the universe during this dark age as a three-dimensional web of filaments and voids, with dark matter and gas flowing along cosmic highways that span hundreds of millions of light-years. The largest void regions, eventually growing to diameters exceeding 300 million light-years, contain less than 1/10 the average density of matter, while the densest filaments accumulate mass at rates that will eventually trigger the formation of the first stars. Temperature fluctuations in the primordial plasma, initially varying by only about 10 parts per million, grow through gravitational amplification. Regions that began slightly denser than average become progressively more dense as their enhanced gravitational pull draws in surrounding matter. Meanwhile, the slightly underdense regions become increasingly empty as their matter migrates toward the growing density peaks. This process of gravitational instability, operating over hundreds of millions of years, transforms the nearly smooth post-recombination universe into the cosmic web that will eventually host billions of galaxies. The first stars ignite when the universe reaches an age of approximately 200 million years. These population 3 stars, as they will later be classified, are fundamentally different from any stars that will follow. Born from clouds of primordial hydrogen and helium with virtually no heavier elements, they can only cool and contract through molecular hydrogen cooling, leading to minimum masses of perhaps 20 to 50 times that of our Sun. Some theoretical models suggest that the most massive population 3 stars could reach masses of 300 solar masses or more, burning their nuclear fuel at prodigious rates and living for only a few million years before exploding as the first supernovae. From your cosmic vantage point, you witness these stellar births as brilliant points of light piercing the cosmic darkness for the first time. The ultraviolet radiation from these massive hot stars begins the process of reionization, stripping electrons from neutral hydrogen atoms across vast regions of space. By the time the universe reaches 1 billion years of age, this reionization process is largely complete, fundamentally altering the physics of the intergalactic medium and setting the stage for the formation of the first galaxies. The deaths of population 3 stars are as dramatic as their births. When these massive objects exhaust their nuclear fuel, they collapse catastrophically, creating explosions that release more energy in a few seconds than our Sun will produce over its entire 10 billion year lifetime. These hypernova explosions achieve core temperatures exceeding 100 billion degrees Celsius, hot enough to forge elements heavier than iron through rapid neutron capture processes. For the first time in cosmic history, carbon, oxygen, silicon, iron, and dozens of other elements are scattered into the interstellar medium, providing the raw materials necessary for rocky planet formation and, ultimately, life itself. You observe as the expanding shockwaves from these stellar explosions trigger new waves of star formation in nearby gas clouds, enriching each successive generation with heavier elements. The metallicity of the interstellar medium, the abundance of elements heavier than hydrogen and helium, grows from essentially 0 to about 1% of modern levels within the first billion years of cosmic evolution. This chemical enrichment is crucial for the formation of low-mass stars like our Sun, which require heavier elements to achieve the precise balance between gravitational collapse and radiation pressure that allows them to burn steadily for billions of years. The first galaxies emerge from this cosmic enrichment process as gravitationally bound collections of stars, gas, and dark matter. These early galactic systems are typically much smaller than modern galaxies, with stellar masses ranging from 1 million to 1 billion times that of our Sun, compared to the 100 billion solar masses of the Milky Way. However, they undergo rapid evolution through mergers and accretion, with the most massive early galaxies growing by factors of 10 or more within their first billion years of existence. Central to many of these early galaxies are supermassive black holes, with masses reaching millions or even billions of times that of our Sun. The formation mechanism for these objects remains one of the greatest mysteries in modern astrophysics, as conventional stellar evolution cannot produce such massive black holes in the time available. Various theories propose direct collapse of massive gas clouds, intermediate mass black holes formed from population 3 stars, or exotic formation mechanisms involving dark matter or primordial density fluctuations. As these supermassive black holes accrete matter from their surrounding environments, they become active galactic nuclei, powering quasars that outshine their host galaxies by factors of 100 or more. The most luminous quasars reach absolute magnitudes brighter than -30, meaning they emit as much light as 10 trillion suns. From your observational position, you witness these objects as cosmic lighthouses, visible across billions of light years and serving as probes of the early universe's structure and evolution. The energy output from these early active galactic nuclei has profound effects on cosmic evolution. Jets of relativistic particles, launched at velocity approaching 99.9% the speed of light, inject enormous amounts of energy into the surrounding intergalactic medium. These jets can extend for millions of light years, creating radio-loud sources that will remain detectable for hundreds of millions of years. The mechanical energy deposited by these jets, combined with radiation pressure from the central accretion disk, can halt star formation across entire galaxies, fundamentally altering their evolutionary trajectory. During the first 2 billion years of cosmic evolution, you observe a universe that differs dramatically from the modern cosmos. The star formation rate peaks at levels 10 to 20 times higher than present-day values, with new stars igniting at a combined rate of several hundred solar masses per year across all observable galaxies. This burst of stellar birth is fueled by abundant gas supplies that have not yet been depleted by star formation or expelled by galactic winds and supernova explosions. Galaxy mergers occur with much greater frequency in the early universe due to the higher density of dark matter halos and the smaller physical separations between galactic systems. You witness dramatic collisions between gas-rich spiral galaxies, events that trigger intense starbursts capable of converting billions of solar masses of gas into stars within time periods of just 10 to 100 million years. These merger-driven starbursts can increase a galaxy's star formation rate by factors of 10 to 100 above normal levels, creating some of the most luminous galaxies in the observable universe. The interstellar medium in these early galaxies contains dust grain populations that differ significantly from modern systems. With lower overall metallicities and different stellar populations, dust formation occurs primarily in the envelopes of evolved stars and in supernova ejecta, rather than in the stellar winds of asymptotic giant branch stars that dominate modern dust production. This results in dust-to-gas ratios typically 10 to 100 times lower than present-day values, affecting cooling processes, star formation efficiency, and the observational properties of high redshift galaxies. As cosmic evolution continues, you observe the gradual assembly of larger and more complex galactic structures. Galaxy groups containing 10 to 50 individual galaxies form through gravitational binding within dark matter halos of masses reaching 10 to the 13th solar masses. These systems eventually merge to form galaxy clusters, the largest gravitationally bound structures in the universe, with total masses approaching 10 to the 15th solar masses and containing thousands of individual galaxies within volumes spanning several million light years. The intracluster medium in these massive systems reaches temperatures of 50 to 100 million degrees Celsius, hot enough to emit copious X-ray radiation that will eventually serve as a probe of cluster mass distribution and cosmological parameters. This hot gas, representing roughly 15% of the cluster's total baryonic mass, is gravitationally confined by the cluster's deep potential well, but can be expelled through active galactic nucleus feedback or merger-driven shock heating. By the time the universe reaches an age of approximately 7 billion years, you witness a fundamental transition in cosmic evolution. The expansion of space, driven by the mysterious dark energy that comprises roughly 68% of the total mass energy budget, begins to accelerate rather than decelerate. This acceleration, first observationally confirmed through measurements of distant type-aware supernovae in the late 20th century, marks the beginning of the dark energy-dominated era of cosmic evolution. The nature of dark energy remains one of the deepest mysteries in modern physics. Whether it represents Einstein's cosmological constant, a dynamic scalar field, or something even more exotic, its effects on cosmic evolution are profound and far-reaching. As dark energy comes to dominate the universe's energy budget, the expansion rate begins increasing exponentially, eventually leading to a future in which distant galaxy clusters will recede beyond the cosmic horizon and become forever unobservable. During this transition period, star formation rates across the universe begin their long decline toward present-day values. Gas supplies become increasingly depleted through stellar processing, while galactic winds driven by supernova explosions and active galactic nucleus feedback expel substantial fractions of remaining gas reservoirs into the intergalactic medium. The chemical enrichment of the interstellar medium reaches levels sufficient to support the formation of terrestrial planets and potentially habitable environments around low-mass stars. You observe as spiral galaxies like our own Milky Way assemble through the accretion of smaller satellite systems and the continued inflow of gas from the intergalactic medium. The Milky Way itself forms through the merger of perhaps dozens of smaller protogalactic fragments, with major accretion events continuing until relatively recent cosmic times. The galaxy's thin disk structure, containing most of the system's current star formation activity, assembled gradually over billions of years as gas settled into a rotating configuration supported by angular momentum conservation. The formation of our solar system occurs when the universe has reached an age of approximately 9.2 billion years, within a spiral arm of the Milky Way where local gas densities and metallicities have reached levels sufficient to support terrestrial planet formation. The molecular cloud that collapses to form the solar nebula contains roughly 2% heavy elements by mass, providing the silicon, iron, magnesium and other materials necessary to build rocky planets like Earth. From your unique perspective outside normal space-time, you can observe the entire 4.6 billion year evolution of the solar system in what seems like moments. You watch as the protoplanetary disk undergoes gravitational collapse and fragmentation, forming the 8 major planets and countless smaller bodies through processes of accretion, collision, and gravitational scattering. The late heavy bombardment, occurring approximately 4 billion years ago, delivers water and organic compounds to Earth's surface, while simultaneously creating conditions conducive to the emergence of life. The development of life on Earth represents perhaps the most remarkable chapter in the cosmic story you're witnessing. From the first self-replicating molecules that emerge in Earth's primordial oceans, through the evolution of photosynthetic organisms that fundamentally alter the planet's atmospheric composition, to the eventual emergence of complex multicellular life and intelligence, you observe the universe becoming aware of itself through the development of conscious observers. The oxygenation of Earth's atmosphere, beginning approximately 2.4 billion years ago, represents one of the most dramatic environmental changes in planetary history. Cyanobacteria, through oxygenic photosynthesis, increase atmospheric oxygen concentrations from virtually zero to present-day levels of 21%, while simultaneously reducing atmospheric carbon dioxide concentrations and triggering the first snowball Earth episodes through reduced greenhouse warming. Complex eukaryotic cells emerge through endosymbiotic events, in which primitive organisms incorporate photosynthetic and respiratory organelles, dramatically increasing the energy available for cellular processes and enabling the evolution of larger, more complex life forms. The subsequent evolution of multicellular organisms, sexual reproduction, and specialized tissues sets the stage for the Cambrian explosion approximately 540 million years ago, during which most major animal phyla appear in the fossil record within a geologically brief period of 20 to 25 million years. Throughout this biological evolution, you observe countless extinction events that punctuate and redirect the course of life's development. The Permian-Triassic extinction, occurring approximately 252 million years ago, eliminates roughly 96% of marine species and 70% of terrestrial vertebrate species, representing the closest life on Earth has come to complete annihilation. Yet from these catastrophic events emerge new evolutionary opportunities and the eventual rise of dinosaurs, mammals, and ultimately human civilization. The emergence of human intelligence represents a cosmic threshold of profound significance. For the first time in 13.8 billion years of cosmic evolution, matter has organized itself in configurations complex enough to contemplate its own existence and origin. Through scientific investigation, humans develop increasingly sophisticated models of cosmic evolution, eventually achieving the theoretical understanding that would allow them to envision the very scenario you are now witnessing firsthand. Human technological development accelerates exponentially following the scientific revolution, with particularly rapid progress in the 20th and 21st centuries. The development of radio astronomy allows humans to detect the cosmic microwave background radiation and confirm the Big Bang theory, while space-based telescopes extend observational capabilities across the entire electromagnetic spectrum and deep into cosmic time. From your vantage point, you can observe humanity's growing understanding of cosmic evolution as scientists piece together evidence from multiple observational and theoretical approaches. Measurements of Type Ia supernovae reveal the accelerating expansion of space driven by dark energy, while observations of the cosmic microwave background provide precise constraints on fundamental cosmological parameters, including the geometry of space, the densities of ordinary matter, dark matter, and dark energy, and the amplitude of primordial density fluctuations. Gravitational wave detectors, beginning with the Laser Interferometer Gravitational Wave Observatory in the early 21st century, open entirely new windows onto cosmic phenomena by directly detecting ripples in space-time itself. These instruments reveal the merger rates of stellar mass black holes and neutron stars, confirm Einstein's predictions about the behavior of space-time under extreme conditions, and provide independent measurements of cosmic expansion rates and distances. As you observe the current epoch of cosmic evolution, approximately 13.8 billion years after the initial moment, the universe continues its inexorable expansion and evolution. Star formation rates have declined to less than 10% of their peak values during the cosmic noon era, while the chemical enrichment of the interstellar medium has reached levels that would have been unimaginable during the first billion years of cosmic evolution. Heavy elements now comprise roughly 2% of the mass in typical spiral galaxy disks, providing abundant raw materials for terrestrial planet formation and potentially habitable environments. The future evolution that stretches ahead from this moment promises changes as dramatic as any you have already witnessed. As dark energy continues to accelerate cosmic expansion, distant galaxy clusters will eventually recede beyond the cosmic horizon and become forever unobservable from any given reference point. Within approximately 100 billion years, only gravitationally bound local structures will remain visible, with the observable universe shrinking to encompass only the local group of galaxies and its eventual merger product. Stellar evolution will continue to transform the cosmic landscape as low-mass main-sequence stars exhaust their nuclear fuel and evolve through red giant phases to become white dwarf stars. The most massive stars will continue forming black holes through core collapse, while intermediate mass stars will produce neutron stars and contribute to the chemical enrichment of the interstellar medium through supernova explosions and stellar winds. On timescales of 10 to the 14 years, stellar formation will cease entirely as gas supplies become exhausted, and existing reservoirs are locked up in stellar remnants or expelled from galactic gravitational wells. The universe will enter an era dominated by stellar remnants, white dwarfs, neutron stars and black holes, with occasional flashes of activity as these objects interact through gravitational encounters or accretion events. Even more distant future epochs promise transformations that challenge comprehension. Proton decay, if it occurs as predicted by grand unified theories, would gradually dissolve all ordinary matter on timescales of 10 to the 34th years or longer. Black holes would eventually evaporate through Hawking radiation emission, with the most massive supermassive black holes persisting until ages of 10 to the 100 years before finally disappearing in bursts of elementary particles and radiation. Yet even as you contemplate these distant futures, the immediate present offers countless wonders and discoveries yet to be made. The search for life beyond Earth continues through increasingly sophisticated techniques, including direct imaging of exoplanetary atmospheres, detection of atmospheric biosignatures, and searches for technosignatures that might indicate the presence of technological civilizations. The nature of dark matter and dark energy remain among the greatest unsolved problems in modern physics, with experimental searches continuing both in deep, underground laboratories designed to detect dark matter particle interactions, and through increasingly precise astronomical observations designed to constrain the properties of dark energy and test alternatives to the standard cosmological model. Fundamental questions about the ultimate nature of space, time, matter, and energy remain unanswered despite centuries of scientific progress. The quantum mechanical measurement problem, the relationship between general relativity and quantum field theory, the origin of the observed matter, antimatter asymmetry in the universe, and the possibility of additional spatial dimensions beyond the three we observe directly, all represent frontiers of human understanding that may require revolutionary new insights to resolve. As your extraordinary journey through cosmic history draws toward its conclusion, you find yourself contemplating the profound implications of everything you have witnessed. From that initial moment of infinite density and temperature, through the emergence of space and time themselves, the formation of the first atoms and stars, the assembly of galaxies and larger structures, the development of planetary systems, and the emergence of life and intelligence, you have observed the universe transforming itself from simplicity to complexity through the operation of physical laws that seem almost designed to permit such remarkable evolution. The anthropic principle suggests that the fundamental constants of physics lie within narrow ranges that permit the existence of stars, planets, and life as we know it. Slight changes in the strength of the strong nuclear force, the masses of fundamental particles, or the rate of cosmic expansion could have resulted in universes devoid of complexity, structure, or the possibility of conscious observation. Whether this apparent fine-tuning reflects deeper physical principles, the existence of multiple universes with varying properties, or something even more profound remains one of the deepest questions in cosmology and philosophy. Your unique perspective has revealed the universe as a vast interconnected system, in which quantum fluctuations during the first fraction of a second ultimately determine the locations of galaxy clusters billions of years later, where stellar nuclear synthesis in the cores of massive stars provides the raw materials for rocky planets and biological evolution, and where the expansion rate of space itself governs the availability of time for complexity and consciousness to emerge. The story you have witnessed is simultaneously one of the most scientifically rigorous narratives humans have developed, and one of the most profoundly meaningful frameworks for understanding our place in the cosmos. Every atom in your body was forged in stellar cores, or during the first few minutes after the Big Bang, making you quite literally composed of star stuff that has been cycling through cosmic evolution for billions of years. The calcium in your bones, the iron in your blood, the oxygen you breathe, and the carbon that forms the backbone of your DNA, all participated in this cosmic story long before Earth itself existed. Perhaps most remarkably, your capacity to contemplate and understand this cosmic narrative represents the universe becoming conscious of its own existence and evolution. Through scientific investigation and theoretical development, matter has organized itself in configurations complex enough to comprehend its own 13.8 billion year journey from simplicity to complexity, from uniformity to structure, from lifelessness to consciousness. This journey from the birth of space and time to the emergence of beings capable of witnessing and understanding cosmic evolution represents perhaps the most extraordinary transformation in the known universe. As you conclude your impossible observation of the universe's birth and evolution, you carry with you not just the knowledge of how everything began, but the profound recognition that the very capacity for such understanding represents the universe's greatest achievement, the emergence of consciousness capable of contemplating the infinite mystery and beauty of existence itself.